Okay, so remember way back when we started this course and we were looking at limits, and we were looking at limits algebraically. So we were doing direct substitution, and we would get something in the form of 0 over 0 or infinity over infinity. And that was a indeterminate form. It didn't tell us what was going on with our limit. And then we needed to go back and manipulate it. So factor it, rationalize the numerator or denominator. There's just different ways that we could go about to manipulate it so that we could figure out what was happening for a limit. L'Hopital's rule is another way that we can deal with these indeterminate forms if we're looking at limits and we get a 0 over 0 or infinity over infinity. This is just another way to approach it. And so let's go through what his theorem says. He says, let f of x and g of x be differentiable on an interval I containing a, and that the derivative of g, so g prime of a, doesn't equal 0 on I, so on our interval for x not equal to a. Okay, so suppose that, again, we look at our limit as x approaches a, and we get f of x divided by g of x, and we got that indeterminate form of 0 over 0, or we got the indeterminate form of infinity over infinity. So if that's the case, and as long as our limit exists at x equals a for that derivative, how we can look at this is take the derivative of our numerator over the derivative of our denominator, and then evaluate that as x approaches a. So this is where you have to be careful, because we've been dealing with the quotient rule for taking derivatives. So notice this is not the quotient rule, and I don't want you to get confused. And then once you start taking derivatives of a quotient, we cannot just take the derivative of the numerator over the derivative of the denominator. So this is just applying his rule. So let's look at some examples. So let's look at that limit as x approaches 0 of sine x over x. We had dealt with this one before in the past, and we saw that this was equal to 1. And we would sometimes use that fact to manipulate our limits as x approaches 0 with sine x in it. And we proved that with using the sandwich theorem. So let's actually go through and do direct substitution. And recall, if we do direct substitution, sine of 0 gave us back 0. And plugging in 0 for x in the denominator, we also got back 0. And so again, that was the indeterminate form. Well, L'Hopital's theorem says that, okay, let's look at the derivative of the numerator all over the derivative of the denominator. So when we're using L'Hopital's, let's put this LH here, saying that this is what we were applying. And so we're going to bring down our limit. We're still taking the limit as x goes to 0. But L'Hopital says we're going to take the derivative of the numerator. So derivative of sine x, recall, is cosine of x, all over the derivative of x, which is 1. And so now when we do our direct substitution and we plug in 0 wherever we see an x in our limit, we got cosine of 0, which is 1, all over 1. Which is 1, which we already knew before we went in, taking that limit, that we should get back 1. We've already dealt with that limit before, but we showed it now using L'Hopital's rule. So our next example, we're looking at the limit as x is approaching -5 of x squared minus 25 all over x plus 5. And if we did our direct substitution and plugged in -5 wherever we see an x, we're going to get the indeterminate form of 0 over 0. So -5 quantity squared is 25. 25 minus 25 is 0. And -5 plus 5 is 0. Okay, so that didn't tell us anything. Before, we would have looked at this and just factored. Let's just apply L'Hopital's rule, though, because that's what we're doing right now. And so that says we can take the limit as x is approaching -5 of the derivative of the numerator. So derivative of x squared minus 25, that's just 2x, all over the derivative of the denominator. And if I took the derivative of x plus 5, that just gives me back 1. So now let's just do our direct substitution. Once we do our direct substitution, we don't write our limit anymore, but we should be writing our limit until we do that direct substitution. And you guys need to be careful because mathematically you want to write things correctly, and especially now that you're getting in the upper division courses. So here we have 2 times -5, and our answer, we would get back -10. So I'm not personally going to tell you what way to solve these. You can go and solve them whatever method you prefer. So you could have started this and you could have just factored, right? That would have been really fast. I could have just factored in my numerator, which was x minus 5, x plus 5, because that's a difference of squares. And I noticed my x plus 5s canceled, right? And then if I went in and I did my direct substitution, I would have -5 minus 5, which also gives me -10. So either way worked. You do whatever method you prefer. But right now, because we're in this section, I'm going to be using Hopital's rule. So what if we looked at the limit as x is approaching 0 of 3 raised to the x power minus 1 all over 2 raised to the x power minus 1. So go in, do our direct substitution. Notice we would get 3 raised to the 0 power. Number other than 0 raised to the 0 power is 1. So we get 1 minus 1 all over 2 raised to the 0 power, which is 1 minus 1. So we get that 0 over 0. So we want to differentiate both the numerator and denominator. Okay. Let's say you forgot how to do that. Let's use logarithmic differentiation. So we know how to take the derivative of natural log. We know how to take the derivative of e raised to the x power. It's just when that base is not e. So if you don't remember, we can quickly get this by taking the natural log of both sides. Let's use our rules of exponents to bring our exponent down front. So we have the natural log of y equals x times the natural log of 3. Now let's take the derivative of both sides of our equation. Taking the derivative of natural log of y, this is 1 over y. But this is the same thing as d times dy dx. Or you could write it as y prime if you like, equals, so the derivative of x times natural log of 3. Natural log of 3 is just a coefficient, a number in front. So derivative of x is just that coefficient in front, which we can just think of as the natural log of 3. So dy dx, multiply both sides by y. So we get y times natural log of 3. Well, y, let's go back and replace what y is. Y is 3 to the x power times the natural log of 3.
If natural log of 3 was the constant value, then what happened to x?
We're taking the derivative of both sides of the equation right here. And so the derivative of, like if I took the derivative of 2x, I just get 2. But this is the derivative of natural log of 3 times x. So the derivative of natural log of 3 times x is just natural log of 3.
Oh, okay, yeah, now I see it.
And so here we can now multiply both sides by y, right, to get dy dx by itself. And y, though, was originally 3x. So we'll just put that in. that was just kind of a long way, but a really fast way that you can remember if you don't have it memorized how to get that pretty fast. And so if I go back in here and use L'Hopital's rule, says we can take, this would be the same thing as if we took the limit as x approaches 0 of the derivative of the numerator, which we just found to be 3x natural log of 3, all over the natural log of the denominator. I can tell right now just by going through this, this is going to be the same thing as 2 raised to the x power natural log of 2. So now when we go in and we plug in 0 wherever we see an x, well, 3 to the 0 is 1. So 1 times that natural log of 3 is just natural log of 3. All over 2 to the 0 is 1. So 1 times the natural log of 2. So this would be the exact form. And I would be happy with that. But if we had a graph or do anything that would help us if we knew what that was. And if we're looking at a limit, it might help to figure out what is that y value we're approaching as x goes to 0. So let's just look at that. Natural log of 3 divided by the natural log of 2. So this is giving me approximately 1.58. So graphically, as x is approaching 0 on the left and the right, we're getting back 1.58. Our y value is getting closer and closer to 1.58. Sometimes you might need to use L'Hopital's rule more than once, meaning that you might get an indeterminate form more than once. So you might get 0 over 0. Take the derivative of the numerator denominator and get 0 over 0 again. So you could use L'Hopital's rule again on that and keep going until that it breaks down where you get some number other than something in indeterminate form. Okay, see if I can do one more really quickly. I don't know, how about the limit? As x is approaching 0 of cosine of x minus 1 all over e to the x minus x minus 1. So right away, I would do direct substitution. That's always how you want to start with your limits. Plug in your value. We're approaching 0, so plug in 0 wherever you see an x. Well, cosine of 0 is 1. 1 minus 1 in our numerator is 0. All over e to the 0 is 1 minus 0. So that's 1. And then minus 1 gives me 0. Okay, so L'Hopital's rule, because this is an indeterminate form. Derivative of cosine of x is negative sine x. Minus derivative of 1 is 0. So I don't have to subtract off 0. All over derivative of e to the x. Derivative of the e to the x is just itself e to the x. Minus the derivative of x, which is 1. Minus the derivative of 1, which is 0. So again, I would do direct substitution. But again, I notice here's the case what I was just talking about. I get negative sine of 0, negative, well, sine of 0 is 0. So negative 0 is 0. All over e to the 0 is 1. 1 minus 1 is 0. So this is where I would want to use L'Hopital's rule again on my answer above. So if I look at the limit as x goes to 0, derivative of negative sine x. So derivative of sine x is cosine x. So I have that minus in front because of the negative. So I have minus cosine x. Derivative of e to the x is e to the x. Derivative of 1 is 0. Do your direct substitution. And so now when we do our direct substitution, we get negative cosine of 0, which is 1. So -1 all over e to the 0, which is 1. So now this is not an indeterminate form anywhere. And so we can look at that the limit as x approaches 0 of this original function is equal to 1 by L'Hopital's rule. Okay, so we'll look a little bit more tomorrow, maybe doing a couple more problems of this, and then probably get into some optimization. So finding absolute, or not necessarily, but finding maximum and minimum values of application problems.